World model. Here is an attempt of this big topic. First, let's discuss, can an LLM build a perfect world model? Let's look at a simple example, Othello, based on a paper in ICLR 2023, Emergent World Representations, exploring a sequence model trained on a synthetic task. Can Othello GPT perfectly learn the rules, or the world model, of the game? Unfortunately, no. From the paper, the main takeaway is that Othello GPT does far better than chance in predicting legal moves when trained on both datasets. Is it possible to learn a perfect model from data? Maybe. For example, for a very simple 3x3 game tic-tac-toe, learn the rule by collecting all possible cases. However, even for such a simple problem, the data may be generated from two sets of rules. This is the system identification problem for the game. Real-life problems are much more complex. In general, a pure statistical method may not be enough. As in the paper, toward causal representation learning, a purely statistical model often provides little insight beyond modeling associations between epiphenomena. Judea Pearl argues in the Book of Why, a pure statistical model cannot climb from association to intervention to counterfactual. It is time to discuss what is a world model. As in the paper The Quest for a Common Model of the Intelligent Decision Maker by Richard Sutton, the transition model takes in states and predicts what next states would result if various actions were taken. The transition model could be termed a world model. As in the paper A Path Towards Autonomous Machine Intelligence by Yann LeCun, the world model module predicts possible future world states as a function of imagined action sequences proposed by the actor. Both definitions include both state transitions and actions. Naturally, the concept of embodiment is relevant. Now we discuss the paper Experience Grounds language. It introduces 5 levels of world scopes: small-scale corpus, our past, for corpora and representations, large-scale internet, most of current NLP, for the written world, perception, multimodal NLP, for the world of sights and sounds, embodiment and action for interaction with physical world, and social world for interaction with human society. Linda Smith and Michael Gasser summarized in the paper The Development of Embodied Cognition, 6 lessons from babies: be multimodal, be incremental, be physical, explore, be social, use language. The embodiment hypothesis is the idea that intelligence emerges in the interaction of an agent with an environment and as a result of sensory-motor activity. Why text and video are not enough to learn a physics model, and embodiment is required? An intuitive example: we cannot learn to swim by only reading books and watching videos. We have to embody with the water and learn the intuitive physics, i.e., the world model for swimming, from the interactions with the water. An argument from the paper may help. We see the need for embodied language with complex meaning when thinking deeply about even the most innocuous of questions: is an orange more like a baseball or more like a banana? World Scope 1, small-scale corpus, is likely not to have an answer beyond that the objects are common nouns that can both be held. World Scope 2, large-scale internet, may capture that oranges and baseballs both roll, but is not the deformation strength, surface texture, or relative sizes of these objects. World Scope 3, perception or multimodality, may realize the relative deformability of these objects, but is likely to confuse how much force is necessary given that baseballs are used much more roughly than oranges. World Scope 4, embodiment and action, can appreciate the nuances of the question. The orange and baseball afford similar manipulation because they have similar texture and weight, while the orange and banana both contain peels, deform, and are edible. People can reason over rich representations of common objects that these words evoke. One approach is to collect lots of high-quality embodiment data and hopefully, learn a decent world model. Alternatively, simulation is a promising, practical approach. Simulators are usually built with rules. However, recently, there emerged data-driven simulators. The paper Simulation Intelligence, Towards a New Generation of Scientific Methods, introduces 9 motifs of simulation intelligence: multiphysics and multi-scale modeling, surrogate modeling and emulation, Simulation-based inference. Causal modeling and inference. Agent-based modeling. Probabilistic programming. Differentiable programming. Open-ended optimization. Machine programming. Note: simulation is simulation. There are usually approximation errors in simulators and learned models. We may have to bridge the simulation to reality gap. Will synthetic data help? It depends. Make sure to handle the simulation to reality gap. Respect the principle of ground truth in the loop. Now let's discuss briefly world model versus AI agents. How to build an agent? There are 3 general methods. First, classical search, optimization or planning methods. Second, data-driven, learning methods. Third, learning plus search/planning methods. AI search methods, operations research, and optimal control are classical search, optimization or planning methods. They are working with a perfect model, or assume so. Data-driven, learning methods include imitation learning, model-free reinforcement learning and model-based reinforcement learning. One more method to build agents is by integrating learning with search, planning. With a perfect model, simulator or a perfect verifier, we can generate infinite perfect data, with a prominent example of AlphaGo. Without a model, usually, we estimate a model. Note: we need to deal with the estimation error. Learning plus search is promising for AI, including LLMs. An issue is evaluation. How to evaluate a world model? How to evaluate intelligence? Comments and criticisms are welcome.